Nested f-tests are a tool that allow us to compare multiple models. So I'm gonna remake a few models here. Maybe I will remove some of my models from my workspace. I'm gonna use RM to remove them. M3. I think I want to keep M full. But I'm just going to put in M1, which is a simple linear regression model, M2, which I think is the one that we were liking the most, and then M3, which is a more complex model. And we still have M full, which was with every one of our predictors. So these are all subsets of M full. And it's important if you're going to do a nested f-test that the models be nested. They have to go inside one another. So you can't compare models that have completely different sets of predictors, but you can test subsets of predictors. And so we're going to use the ANOVA function, which we've used before. We've done ANOVA on M1, something like that. But we're going to do ANOVA, and then we're going to give it a bunch of models, and we're going to put them in ascending order of complexity. So the smallest model, then the next, and then the full model. And if I run this, I'm going to get a different sort of ANOVA table. So I get some of the same things. I have degrees of freedom for each of these models. I have sum of squares. I have an F value and a P value. But I'm getting like the residual degrees of freedom, the residual sum of squares, and the table is just laid out differently than what we've seen before. Just so that I can point things out better, I think I'm going to switch back over to the iPad for a minute. All right, so I'm going to drop in a screenshot from R. And maybe I will also just white some of that out so it's a little less distracting. Okay, so we talked about the equation for the F value. And the way that it works is it makes the comparison with the full model and the reduced model divided by the difference in the number of predictors over the SSE for the full model divided by n minus k minus 1. So let's think about what's going on in each of the rows of this table. So not all of them have every one of the values. So if you look at the first row, it actually only has 2 of the numbers. And then the second row is a comparison row. So this is comparing M2 to M1. So we're saying, is the model with weight and age better than the model with just weight? So what this table is giving us in the sum of squares column, this is that difference, the difference between the SM full and the SSM reduced. And so if we wanted to reproduce these F values, our F statistics, we could do, like, for example, comparing M2 to M1, F is equal to 49.704 divided by the difference in the number of predictors, which is 1. We have one more predictor, over the SSE for the full model, which is the RSS from the bottom, 2.156 divided by, and then it's going to be the 20 minus the number of predictors in the full model, which is 1, 2, 3, 4, 5, 6, 6 minus 1. So this would be 49.704 over 2.156 divided by 13. And that comes out to be 299. Which is the number in our F column. We could also do the comparison here. So let me just move this down. This is comparing M3 to M2. And for that one, we would do the F would be the 0.279 divided by 2 over 2.156 divided by 13. And that comes out to be 0.84. And then the last one is comparing M3 to M full, and that would have an F value of 2.389 divided by 2 over 2.156 divided by 13, and that comes out to be 7.2. So reading the ANOVA table is a little bit strange because the p-values that come out are just about the comparison of two models. So comparing M2 to M1, is M2 better? It has 3 stars, yes. M2 is better than M1. So maybe I'll write that down. M2 better than M1. Then this p-value is comparing M3 to M2. And is it better? No, it has a large p-value. So M3 no better than M2. But then we would have another p-value, and this would be comparing M3 to M full. Is M full better than M3? Yes. M full is better than M3. So it doesn't really tell us which one is the best. I know that M2 is better than M1, and I know that M full is better than M3, but if I actually wanted to compare M2 and M full, I would have to run this again without that M3 in there. Maybe I'll go back to R to actually try that out. All right, so we've looked at this table, but maybe we just want to have the ANOVA of M1, M2, and M full. And now I can see that M2 was better than M1, and M full is better than M2. So I would probably pick the M full based on these p-values. So from the ANOVA above, we're not sure whether to pick M2 or M full, but we can run the ANOVA code without M3 to be more certain. And I'll put in a code chunk, and then let's put in this here. Now we know we prefer M full based on the amount of variability that it can explain. So again, this is one of those places where a human analyst is totally necessary. When we were going through the modeling step by step and looking at the variance inflation factors, we decided to pick, I think, M2. And we said, you know, it wasn't sad to lose the tiny bit of R squared based on these additional variables because we got better normalcy and we got a simpler model. But by using the nested F test, we would actually prefer the M full. So we really need a human in the loop. So just like with the regression summary table, we can try to compute some of the numbers in an ANOVA table ourselves, just so that we can make sure that we know where the numbers come from. So let's consider a simpler ANOVA table just for 2 of the regression models. I'm going to do the ANOVA, the 2 that we like, M2, and then the full model. And I'm just going to try and compute the numbers in here. So I'm going to do a little bit of base R code. I'm going to find the mean of blood P $BP. So that's the blood pressure. Let's see, mean BP is 114. And then I'm going to find the SSM for the full model. So that's the fitted values, the YI hats for the entire model, minus the mean. And I'm going to square those and sum them up. I'm going to do the same thing for M2, square those and sum them up. And then I can look at those. So I've got SSM full, I've got SSM reduce, and those numbers don't appear in the ANOVA table. Those, 557, 555, but the difference between them does. So if I do the difference between the SSM full and the SSM reduce, that's that difference that's appearing here. So it's the additional sum of squares, model sum of squares for my larger model. But I want to know, is that statistically significant? And to do that, I need the SSE, which is the sum of the residuals squared from the full model. So that was the SSE full, the 2.155. And then I could find this F value by doing that difference in the sums of squares of the models divided by the number of additional predictors, which was 4. We had 6 variables here and 2 here, so that's additional 4 predictors, divided by the SSE for the full model, divided by the n minus p, which was 6, or k, sometimes we're calling it, minus 1. If we do that, that's our F value of 4.022. So that's how we could compute things in that ANOVA table. All right, so that's all I've got for the end of chapter 3. The nested F-test is another tool in your toolbox for helping you choose models, but it's no replacement for a human analyst.